Welcome on today's session that will be dedicated to verification of IDEA StatiCa 2D detail against to also our in-house solution IDEA StatiCa RCS that is based on the different assumptions for simply supported pre-stressed concrete beam. So my name is Lukas, and I work as a computational validation engineer in company IDEA StatiCa, and I will take you through this presentation. Um, Something about the content briefly. We will talk about the global model because this is like a pre-stressed beam, some construction stages, how it's being considered, also, what section has been chosen, has been selected for code checking and why, and defining the construction stages in the RCS. So it's like a part of the presentation that is very important. And also the modeling in IDEA StatiCa 2D detail, mostly the results and the assumptions that's been got into the solution, and the output is a comparison in between the RCS and the IDEA StatiCa 2D detail from the perspective of the stresses on like a concrete, stresses in the reinforcement and stresses on the tendons. So this is like a whole agenda that we will go through at this session, and something about the abstract. Actually, I just call it abstract because I would like to summarize what you can looking forward. So this session presents as and like in-house verification comparing two IDEA StatiCa approaches. So on the same simply supported pretensioned beam, so the section of the RCS or the section in general has some dimensions. I mean, the width is 250 millimeters. The height is 1,200 millimeters. As you can see, that's been reinforced by the stirrups with the diameter 12, and there are also like equally redistributed reinforcement longitudinal bars along the length of the beam with diameter 16, and also the tendon. The tendon is made from the material Y1860 S7 with the wire like a diameter or the strand diameter 15.7 millimeters. So as you can see, that is just the one tendon because we want to simulate it and make it like a straightforward and make it clear to clarify and advocate the results sensibly. So concrete and tendon stresses as the output will agree like until 3%, while reinforcement stress like diverges up to 15%. I will talk about it later, why there are the discrepancies, and I show that this difference is not an error but a documented modeling choice. The reason will be like a tangent stiffening that is applied on the reinforcement rebars for IDEA StatiCa 2D detail, and it leads to like a different plane of strain, and the neutral axis has been shifted, and you will be able to observe why basically the stress level in the reinforcement is different. So before we compare all the numbers and I would like to mention the assumptions because it's worth being clear on what each tool actually assumes, differences between the RCS or beam in general and IDEA StatiCa 2D detail. So because that's as I mentioned, that's every difference comes from. So RCS, the beam approach is sectional check. So it works in like a one dimension, plane section stay plane. There is a perfect bond between the steel and the concrete carries no tension for ultimate limit state. So you give it the internal forces at the section, so that are coming from the linear calculation, linear model that we have in different, like in some finite element software, and it returns the stresses, strains, and the tension stiffening only enters the crack wave calculation. That is not the point at this presentation because we are verifying the ultimate limit state. So on the other side, detail is different philosophy. It's like a 2D model, plane stress built on the compatible stress field method and continuous stress fields in which equilibrium and compatibility are solved. So they are solved simultaneously across the like entire region. So uh, crucially, it accounts for like a tension stiffening directly in the reinforcement behavior. The concrete between the cracks still carries the tension that is basically that is associated in this on the diagram of the reinforcement rebars. So you will see like a different diagram of it, where the tension stiffening is involved. Um, so we have a same physics to idealization. So keep the distinction in mind that the results will make complete sense once we do. Okay. So let's move to global model. Actually, as I mentioned, the total length of the beam is like 10 meters. The beam section is, I will repeat it up, width 0.25, height 1.2 meters. The tendon is like a shifted, basically from the is shifted from center of the gravity of the section here. uh, this is 450 millimeters. Oh, apology. This is 450 millimeters. The concrete grade is like a C30/37. That's like a standard concrete. Maybe it once I used like a higher strength, it would be better, like a more standardized to like a engineering practice. But we just use the C30/37 for this exemplary like example. Um, and the pre-stressing strands, as I mentioned before, Y 1860 S7 with the wire diameter 15.7 millimeters. So those are the inputs that been used for the analysis. Um, and what about the loads that is used? As I mentioned, there are like a construction stages. So there are like four loads that are coming in different stages. Actually, the first loads is like a dead load, or we can say like a self weight that is uniform line load 7.5 kilonewton per meter. um, the anchorage stress for pretensioned like a wire, there is like 1100 megapascal. So the level of the stress is like it could be higher, but if you imagine there will be some like a increment of the loads, like a permanent and a variable, so it will increase the stress on the tendons, and we need to having like passing all of the checks. So 1100 megapascal is like base level that is like a sufficient to all of the code checks passing well. In the like a second construction stage, there will be like a permanent load of the 20 kilonewton per meter, again uniform load, and variable load at the end, or yeah, at the final stage, 15 kilonewton per meter. So to make it proof or provable, that it behaves as a simply supported beam. So you can see that the self weight actually, that the self weight is 7.5 kilonewton meter. If you calculate it uh, very simply with this equation, so you will receive the maximum bending moment here. As you can see, the shear in the bottom is basically zero, and for like a prestressing, there is some axial normal force, and the normal force, as you can see, is minus, I would say, 164 kilonewton. This is the normal force, and we can also observe the bending moment that has like a constant shape because the tendon is like a straight. So there is like a minus 73, yeah, 73.5 kilonewton meter along the length of the beam. So this is what we got, and we can move forward to permanent load that is evoked the 250 kilonewton meter in the middle, and variable load with 15 kilonewton per meter. It's declared by the 187.5 kilonewton meter that is coming out of the simulation. Um, okay, so what will be the analyzed section and why? So, as I mentioned, like before, we will analyze or doing the code check based on the two different models. And the 1D model, if you will analyze the area where the plane of strain is violated, the linear plane of strain is violated. So it means where if it's close to the discontinuity region where this plane of strain um, assumption is not valid at all. So you will receive completely like a different results compared to IDEA StatiCa to the detail because the method for like a beam solution is insufficient for this discontinuity region. So this is, for example, the area that is in the very close to the support, where if you make a strut and tie, so you will receive the proper behavior and the code check. But if we will analyze the area in the middle where it's like a zero level of the shear forces, and that's very far from from the boundary condition, and it's not like a discontinuity region design where we can assume that the linear plane of strain is guaranteed, so we can analyze and compare those two solutions. So what I did, I just printed out the values for self-weight, pre-stressing, permanent load, and the variable load. We can see the normal forces, shear forces, and the bending moments. Everything is like extracted. This is like a plane forces, this is like a 2D. It's reduced to the like a 2D XZ plane. So here is a X, here is a Z. So all the actions like a forces are stepping into the calculation with in this regime only in the plane. So what we got? We got all the moments, shear forces, and the normal forces that are important for as the input to IDEA StatiCa RCS. Okay. What about the construction stages? As I mentioned, we I used the construction stages, but what I removed are the like the artifacts that can like bias the results. I mean, um, I mean, uh, you know, there is happening like a short term and long term losses. For concrete, if you pre-stress it, also for reinforced concrete, there are some like short-term and long-term behavior of the concrete. So once there is like a pre-stressed tendons, we are also accounting the losses on the tendons that are later on projected to like some staged behavior of the concrete, because in the relevant time there will be like a different creep and the shrinkage, different losses, so the beam will behave differently because the stress is decreasing because of the losses. So to eliminate or alleviate the effect of the short-term and the long-term losses, I just removed from the analysis the short-term and the long-term losses assumption, because you're able to turn it off. And what like remained, what remained only the elastic shortening, because this is the like a property or the feature of the beam itself. So if the beam itself has some stiffness and you will pre-stress it, it will make some shortening of the structure because of the deflection. So also the tendon will experience some losses that you're not able to just very easily eliminate. So this is one of the artifacts that can lead to a little bit like results differences, um, in between those two solutions, but that they are very minor. But as as the variable, we need to consider that. So and of course, the tendon stress is increasing based on the increment of the loads that is applied on the top of the beam. So you will be able to see, because there is a higher deflection, so there is like an increment based on the increased deflection due to the load. So it will be also projected into the stress on the beam or on the tendons. Okay, so once we step into to RCS, we need to select the stage section, where you need to set up the construction stages. As you can see, I just selected the construction stages in the 28.01 and 28.2 days. So those those like a time frame is very close to each other, so there will not be the differences in between the results from the point of view of the losses. And as I mentioned before, the creep and the shrinkage are like a turned off, so there will not be like more involved in this calculation. So you need to also like bend up the software a little bit, like remove the creep coefficient also in the RCS to emulate the behavior you want. But what is important are the increments of the loads. So as you can see in the 28th day, I'm consider all the time the consistent stress. This is just the assumption only for this verification, because the stress level is the stress level, oh, pardon, the stress level is yeah, that's here. The stress level is, of course, varying over the time. But for the purposes of the comparison, I would like to keep it constant, like a 100 and 1000. So in all the stages, there is like anchorage stress. So that's also prohibited in the normal force and the bending moment. So you can see those are two internal forces um, that are coming from the primary effect of the pre-stressing. There are no secondary effects because this is like a simply supported beam. And as you can see, those values, that's for example, this is from the self weight, I need to add as the first increment. Also, this value is projected here, and permanent is projected here. Here at this step for action stages, you're just assigning only the permanent states. as you can see, permanent states and the pre-stressing that is projected in this step. But if you want to add also the variable loads, you need to like click through the internal forces and add it as a separate load. So this is how it's been added actually to RCS. In the next session, I will be introducing the modeling approaches and how I like inserted all of the inputs into the RCS and the 2D detail. So it will be in the follow-up videos that we will talk about it more in detail. And at first, the response in the 28th day. So once I will put just the self-weight or the dead load plus the pre-stressing, I'm able to display three level of the states. I would say this is like an initial state that you're able to account it, like this is like a linear stress where it's like a normal force bending moment with that is composed or consists from the self weight plus pre-stressing. Um, and in this increment there is like an increment that is coming from the self weight. Okay, and this is the final state because if you account those two values, you can see here is a plus, so you will receive the final stress on the tendons, final stress on the rebars, and this is the plane of strain, and this is the total strain on the rebar and on the tendons. So we can observe that there is like a minus 0.4 times E minus 4 for epsilon x, and for stress level minus 0.8 megapascal. So the anchorage stress has been increased due to the sulfate just about the 2.3 megapascal. So this is not big changes in the tendon stress. What will happen if we apply on the top of that to this delta sigma? This is the increment that is coming from the permanent load. So once we apply this increment, we will receive the stage where the structure is basically cracked, and there is not like a decompression. So you were able to see that the plane of strain works along the height of the um, section linearly, because this is the one of the assumption that is the linear plane of strain. If once you're far from the discontinuity regions, you are able to consider and account those effects that are like a linear plane of strain. So this is embedded inside the or embodied inside the theory that is for section or for 1D beam or RCS. So you're able to see that there is like approximately 200 megapascal increment on the tendons, and also there is like a completely different stress state with minus 8.1 megapascal on the top, and the maximal stress on the reinforcement is 215, and on the tendons 1241 megapascal. So in the third stage, we just added to the delta epsilon delta sigma r the effect and the outcome of the variable load. So once we have it, so you are able to observe that here is approximately minus 10.9 megapascal, and here is 413 or 414 megapascal in the rebar, and there is also increments from the point of view of the stresses on the tendons. So as you can see, that's working really well. Once you're adding like a more and more the loads, you're able to observe the more and more ascending stresses that's are basically in the section, and also you're able to see how the neutral axis is also changing. You can see here's a 338. So once I will apply more loads, so the neutral axis is like shifted up. So before there have been like a more level of the stresses, and right now that's been like a reduced. That's been like a reduced the neutral axis or this compression zone. But of course, you are heading uh, to the part of the material diagram that basically looks like that. So we are somewhere here. So this is like observable from the stress evolution on the section itself. Uh, so this is um, this is where we are, and we are moving to IDEA StatiCa to the details. So I just replicated the reinforced section or the reinforcement I just applied to the whole model that is in total 10.3 millimeters length, because the 10 millimeters is from the center of the support to the center of the support, so the total length is 10.3 meters, because the width of the supports is zero point 0.3 meters on one side. Here is a zero point 0.3 meters on the other side. So if you take it from the in the middle, that's in total here, or in the middle there is like 10 meters, but in total there is like a 10.3 meters length of the beam. So there is populated also the reinforcement rebars. There is also accommodated the part of the tendon that is embedded inside, and it looks basically like that. It's a 2D plane stress solution, compatible stress field method. Again, same physics, but a different approach. This is the higher level of the modeling, with material nonlinearity and tension stiffening, with consideration of some bond effects that are also affecting the results, and changing the behavior of the whole beam. Okay, so once we analyze the beam in the 28th day, at this stage there is like a pre-stressing plus the permanent load, or not plus the self-weight. Yeah, this is the first load case, or first construction stage, where it's just the self-weight plus pre-stressing. So this is my stage, and as you can see, the critical value is not here. This is in the area where it's in the discontinuity area, because it's very close to the support. Those like I would say effect is hardly to capture for this 1D solution. It should be analyzed here, because the plane of strain assumption is violated, and it's not valid at all. And but if I want to see what is happening here on the top of the surface, or top fiber of the reinforced concrete, or mostly on the concrete surfaces, I'm able to see that there is like a minus zero point 0.8 megapascal. So once I compare it with the solutions that we had here, as you can see, this is the same value, minus zero point 0.8 megapascal. And on the reinforcement rebars, here at this position we have minus 2.6 megapascal. The beam is like a fully pre-stressed, so we can observe that it looks basically like that. So this is the level of the stress uh, on the detail. Um, the stress that is outlined here is called sigma 2, and this is the minimal principal stress under compression that is composed, from the tensors as sigma x plus sigma z plus tau x z. Of course, there is like a combination rule for the principal stresses that you need to account, but those three tensors of the stresses are stepping into the final outcome that is like a critical the maximal principal stress under compression. So, what about the tendon? Tendon stress is 1097 megapascal, and we can basically move forward. So in the second construction stage, it's about the like zero point 0.1 day later, we can observe that because there is like right now the sulfate plus prestressing plus permanent. So on the top is like a 20 kilonewton per meter, and you're able to observe that the stress on the top here is 7.8 megapascal under compression, and in the bottom rebars, the maximal stress is 182.3 megapascal. Also, the stress level in the tendons has been marginally increased thanks to the additional loads that's been added on the top of the beam. Once we move forward to results for like a final stage where is considered the variable loads, you can see that the stress level is minus 12.5 megapascal. So the solution is analyzed for like a default mesh settings with the number one. If you decrease the default level on the zero point 0.5, the stress will increase from minus 2.5 to approximately 30 minus 30 megapascal. So you'll be much closer, or you'll be closer to section solution or to RCS solution. But everything is dependent on the mesh sides, so we highly recommend to utilize the default settings for standard cases. One, because that's been verified based on this assumption, and there will be done some sensitivity studies for the mesh setup. As you can see, also the stress on the tendon has been increased from this point to this point. As you can see, there is the increment delta that is observable. Okay, so once we have everything, we can compare the results. And where are the regions where we were comparing the results? So the area at first for concrete incompression in the top fibers. So this is my level where I was comparing the stress under compression. There is just the one tendon, so we will compare the results in the tendons. And also the rebars in the tension in the bottom layer. Yeah, so this is like a mostly demanded part, and is like is getting the biggest stress level that is crucial. Okay, so once at first, let me start with the concrete under compression. So you can see the blue line is representing the RCS, the orange line is detailed 2D, and the dashed line with the triangles labeling is the error. So we can compare that those two values and those two values are reaching maximally like a 3.7% discrepancies in between those two results. So I would say that's are like a great results once we are comparing those two solutions. Once we move to the rebars, or at first let me start with the tendons. So in the tendon, the discrepancies in between the results in each construction stage are till like a 2.7% maximally. That's I want to announce that's like a great match in between those two results, and the biggest discrepancies are like lying on the or uh, yeah, are lying basically or laying on the or are leaning basically on the rebars. Why? You will or at first the values. As you can see, the discrepancies in between the stresses are till like a 15.3% for like a permanent stage, where been like the biggest increment, and till 10 or 10.5% for the variable load case or additional increment of the variable load case. I mean, this is the end of the design working life for this task or for this beam, and this is the last increment from the that that is like a variable. So we can see uh, that basically this is the biggest portion of the discrepancies is leaning on the rebar. So why is this happening? So let me give you some like key takeaways that are basically coming out of this in-house verification. So at first, the concrete and the tendon, concrete stress and tendon levels are matching all over the construction stages, and give like reasonable trust that the solution is perfectly aligned. Um, there is like a stress differences on the rebar. Why there is like a till 15% discrepancies. So this is basically the statement that is written here, that the rebar gap is due to the tension stiffening and different plane of strain. So once the tension stiffening is activated, there is like a partially contribution of the on the concrete in the tension that is basically applied on the material model of the reinforcement rebars, and this is the reason why, because for like a section or for RCS, there is like a perfect bond, and the material diagram for reinforcement rebars basically looks like that. But once we take into account the detail, so the detail basically, this is like plain rebars that are the same as for the RCS, but our model basically looks like that. So there is like a level of the tension stiffening, and the tension stiffening is happening basically under this curve. So if you just like, I would say, like integrate in between those two definite part, you will see the contribution of the I would say tensile stresses that are considered like a 0.67, because we are considering the averaged value of the stresses. So this is like a two-third value, and you will be able to see that those I would say contributions of the tensile stresses that are based on the reinforcement ratio, because the curves is different for different reinforcement ratio. So they can be up to like a 15% if you compare it with the standard solutions that are coming for like a standard naked bar, and different assumptions that we have like in the RCS. So the both approaches, this is very important that both approaches are valid, because the beam theory and CSFM give the same overall results but differ in the reinforcement stresses, and the differences are based on the different assumptions for reinforcement rebar diagram that considers tension stiffening. So I would say like a high level of the or high level approaching or approach for 2D detail brings up like a lower level of the stresses on the reinforcement rebars, because some of the tensile stresses are consumed by the portion of the tension that is basically at this area and is applied on the reinforcement bars. So That's all basically for from my side, but I would like to emphasize that I've been endorsed as the certified trainer. So once you wanted to discuss some topic or you will have some doubts, so you can just contact me on the Struckinside at gmail.com. I'm quite active on the socials, so you were able to follow me on the LinkedIn, where I'm just posting everything what is happening in the company from the point of view of the development and some new features. What is in general, what is like a status of IDEA StatiCa from my perspective, and that's basically all. Thank you for attention, and I would like to mention that in the next chapter I will take you through this modeling approaches in the RCS and to the detail to emulate uh, the the outputs that I showed you.